Imagine you're a teacher and you need to keep track of 100 student test scores. If you try to store each grade as its own completely separate piece of information, things get messy fast. In programming, we call these individual pieces of information variables. If you have to create a brand new, uniquely named variable for every single test score, your code becomes incredibly difficult to read. You can't easily find the class average, and just keeping track of all those names is a headache. To fix this, programmers use something called an array. Think of an array as a neatly organized structure, like a row of connected boxes. Instead of 100 loose variables, you now have one continuous block where all those related test scores live right next to each other. This diagram shows exactly how we build that row in code. We give our data block a single name, like scores, and tell the computer exactly how many boxes we need. Now, one line of code neatly packs all those grades into a single organized unit. By trading dozens of separate chaotic variables for one structured array, writing your code becomes much simpler. You only have to keep track of one name to manage the entire group of data. When you look at this diagram of our connected boxes, you'll notice something a bit unusual about how they are numbered. In programming, computers usually start counting at 0, not 1. So our very first test score is placed in box number 0. These position numbers are called indexes. If you want to check a specific student's grade, you just ask the computer to look at the exact index number. Here, asking for index 3 instantly retrieves the grade of 100. You do have to be careful with these positions. Because our 5 boxes are numbered 0 through 4, asking the computer to open box number 5 means reaching for a position that isn't there. In coding, this is called an index out of bounds error, and it will cause your program to crash. Keeping track of the exact size of your array and remembering that it starts at 0 is a strict rule you have to follow to keep your software running smoothly. The reason arrays are so fast comes down to how they are built inside the computer's memory. When an array is created, the computer finds a completely empty block of space and bolts those digital boxes together in a straight, unbroken line. This unbroken line is called contiguous memory. Let's look at the X-ray blueprint of these boxes to see how the computer navigates them. Every spot in a computer's memory has a specific address, like a house number. If the computer knows that box 0 starts at address 100, and each box takes up exactly 4 units of digital space, it can find any other box using simple math. Add 4 units to get to the next box at 104, and 4 more to reach 108. Because the spacing is perfectly predictable, the computer never has to waste time opening the first 3 boxes to find the 4th one. It just takes the starting address, adds the required space, and jumps straight to the exact position. That predictable layout is the architectural superpower that makes an array lightning fast when you need to pull up a piece of data. Finding a single grade is easy when you know its exact index number. But what if you want to find the highest test score in the entire class? To do that, we have to look through the whole row, one by one. In programming, we automate this process using a tool called a loop. This diagram shows a loop in action. We tell the computer to start at index 0 and check the value. The computer keeps a running tally on a scoreboard. It moves to the next index, compares the new score to the scoreboard, and updates the tally every time it finds a higher number. Pairing an array with a loop gives the computer a systematic way to scan through millions of items in a matter of seconds. It is the primary method computers use to search, sort, and process large amounts of data. Sometimes you need to update the data inside your array. Let's say you want to be a generous teacher and give everyone double points on their test. You might write a specific piece of code called a function to do exactly that. Instead of handing that function a heavy, redundant copy of all the test scores, you use a method called pass by reference. You are simply handing the function a digital tag with the memory address of the very first box. The function follows that address back to the original row and makes its changes right there. Updating the original boxes directly is incredibly efficient. It saves a massive amount of system memory because the computer never has to duplicate your data just to make an update. So far, we've only looked at a single row of students, but what happens when the school year starts and you need to keep track of 5 different classrooms at the exact same time? To organize that, you can stack multiple rows on top of each other. This diagram illustrates a 2-dimensional array. It works exactly like the single row of boxes, just expanded into a structured grid of rows and columns.
To read through this larger grid, we use a loop inside of another loop. The outer loop selects the first row, and the inner loop reads across every column in that row. Once the row is finished, the outer loop drops you down to the next row, and the scanning starts over. These grids are everywhere in the software you use every day. They are the underlying structure behind digital spreadsheets, and they map out the coordinates for entire worlds in video games. When you strip away the graphics and the buttons, anytime you see a massive list of data, a global high-score leaderboard, your shopping cart, or your character's game inventory, you are looking at an array. The efficiency of that data relies entirely on the fact that those digital boxes are physically connected in memory and mapped out with predictable math starting at position 0. Mastering this simple row of connected digital boxes is the first step toward handling any amount of data. Whether it's 100 student grades or millions of map coordinates, the principle remains the same. Keep the information connected, predictable, and fast to find.